There are transistor schematics in the handout, the printout from Wikipedia, so you can take a look at that. But the big thing, again, is to look at the waveforms and see how are the waveforms defined. And that's in here. So this is the example of my Simulink design for Class A. Now, here I've got a signal generator, which is a sinusoid, a slider to determine gain, and that is representative of the volume control circuit, right? Well, when we look at the 2-amp examples later, we'll see that the way that's implemented is you've got a preamp stage that buffers the guitar signal, you've got a voltage divider, volume control, and then you've got additional gain stages. And so all that is kind of bundled into this ideal slider gain. That determines our gain. You've got a bias point, right? Because in this example, I've defined the power supply rails as 0, ground, and 100. So you need to bias it in the middle for operation. So I've added a bias of 50 volts, or 50 something to this Simulink. So what we've looked at, so we can look at it here, and we see that in the Simulink model, I can attach a scope before saturation. So saturation is trying to model power supply rails, right? If you're building a real amplifier, you can't have infinite gain or any arbitrary gain. Your maximum gain is before clipping is determined by the rails. So you can create gain, and if you go beyond the rails, then you clip the top and bottom. So you've still got gain within the linear region, but then you're clipped at the top and bottom. Okay? So these are the conceptual blocks that I've defined, and you could, like I said, kind of map them to devices that the transistor has its inherent saturation. The biasing, of course, would be done with resistors. You can see how that works when seeing amplifiers in previous classes. The thing to note here is Class A amplifiers are the least efficient. Okay? And if you look at it and you think about what I just said about the bias, you can see why. Okay, you need to bias it so that you're far away from cutoff at the top end, cutoff at the bottom end and saturation at the high end, right? You need to bias your transistor so that it's always on, that it has a quiescent current. So the problem is, when you've got no signal coming in, you're wasting power because you've got it biased in the middle. So it's not an efficient device. So you definitely want to avoid Class A for high power for two reasons. One, because it's not efficient, and two, because your output devices are on all the time. They need to dissipate power all the time, right? If you can shut off your devices, a device only dissipates power when it's conducting. So if you can shut off the device for half the cycle, you're dissipating half the power. And that's the idea of the Class B and Class AB. And if you take it to the extreme, you get the Class D amplifier. Okay. Another important thing to note is the way I have this model, the saturation is symmetric. When in reality, if we're talking about transistor, right, it uses an exponential curve. So your saturation in cutoff is different, or excuse me, your clipping cutoff is different than your clipping in saturation. If you run against the bottom versus the top, you'll get different things. So you have asymmetric clipping. And we'll look at that next week when we talk about pedals. That's a very useful feature in certain pedal designs. The fuzz face, its characteristic sound is based on asymmetric clipping. And remember, remember, we haven't seen it until next week. One interesting thing about symmetric versus asymmetric clipping is symmetric clipping only introduces odd harmonics. Asymmetric clipping can introduce even and odd harmonics. And that comes straight from Fourier analysis of the symmetry properties.
What do you mean by asymmetric clipping? Like, how is it asymmetrical? The top and bottom?
Top and bottom would be different. So if you've got, this is your sine wave. Symmetric would say you clip at 70% on both. Asymmetric might mean you're clipping at a different level, or it could also mean just the way you're clipping, because I'm showing idealized hard clipping. It could be how you clip. It could be, you know, what this looks like. And again, that all affects the frequency components. So it could be that because of the circuit, it clips hard on top and softer on the bottom. Or it could be that because of the device, it goes into clipping fast, but it comes out of clipping slow, so you get this slewing. You know, there are all kinds of variations, and they all have a different tonal effect. But, you know, this is all part of Class A versus Class AB distortion when people talk about that. And it's also, truthfully, it all depends on the amplifier. You can talk about Class A or AB, but every amp sounds a little different. And even the same model amp may sound different from unit to unit, based on the values, based on the tolerance, and based on the tube. Okay, Class A amps, again, like I said, you don't want to use Class A in high power designs because they're inefficient. So the flip side of that is these are really common in low power designs because they're cheap and they use less parts. For instance, you can create a Class A amp with one output, two one-output transistors. You can't create a Class AB amp with one output device. It's just not possible. So it's the only thing that allows for single-ended output, but still amplifies the full waveform. Now you can use multiple output devices in Class A too. That all depends on how the bias is set up. Okay? Well, I'll hold off the demos for the end. So Class A outputs. So if I look at this, what's the problem with this graph?
Problem?
Yeah, why? I'm putting in a sine wave, and I'm getting out this. Why?
Because you don't have a negative rail.
Well, that's it. Or assuming that my rails are ground and 100. It's
It's
it.
off in a negative part of the loop.
Right. And the reason why is because it's not biased.
It's not biased.
Right. You could do it like you're saying and have a plus and minus rail. But typically what you have is a ground and a high rail, and you bias the DC up. So yeah, so in this example, I've left it biased at 0, where it really should be biased at 100. Now the problem with this one, right, it's biased correctly, it's centered at 50, but what's happening?
Gain's too high.
Yeah, gain's too high, it's clipping. So here, I'm driving it into saturation at both ends. And again, since I did a symmetric model, it clips equally. And then if I reduce the gain, boom, you get the sinusoid we expect. So, you know, there are a number of things with the Class A. Obviously, if you're designing the circuit, you need to design the bias correctly, and you need to watch the gain for clipping. Now, again, because we're talking musical devices, maybe adjusting the bias and the gain are to get a certain type of clipping. You know, whereas in your electronic class, you're always concerned with staying linear, not distorting. You would always bias at the point to give you maximum voltage swing, and you would always reduce the gain to keep away from clipping, even under the worst situation. You have to have good headroom. Here you may want a specific distortion. Or you may even want to be able to give that as a user control. You know, bias is rarely brought out as a control on an amplifier, but with a lot of effects pedals, that's a common modification. And you put that in there so people can play with doing these kind of things and see what kind of effects they get. Okay, so the graphical transfer function, this is kind of collapsing that whole thing into another summary. Have you seen transfer functions before like this, represented like this? Transfer function is kind of an overloaded term, right? You think of it as an equation in terms of S that you evaluate with a loss domain. That's what we normally mean with transfer function. Well, this is a graphical transfer function. And it's quite simple. It's a curve where you draw a straight line, or you often approximate straight lines. Your input goes in one way, and it gets reflected. So you consider this as a mirror, and then it comes out that way. And we'll see next